So that brings me on to the next part of today's talk. So we're very excited to be able to introduce Daniel Warput to talk about his work on contextual inference. So Daniel, thank you very much for agreeing to talk today, and I'll hand over to you.
Thank you so much, Josie, and thank you to the organisers for inviting me. It's a real pleasure, as someone who doesn't work in robotics, to be able to talk to you. I work in neuroscience. I study how humans learn to control movement, particularly focusing on motor learning. We tend to run a very active lab. We bring people in and get people to do motor learning experiments. But because of COVID, the lab has been shut for 2 years. So you're going to see what happens. You stop as neuroscientists doing experiments and make them do theory instead. So I'm going to present to you a model which we've developed over the last year or so, really trying to understand how humans learn the repertoire of motor skills over the course of their life. And so, as a British person in New York, I think a lot about making tea. And as you make tea, there are different steps you have to go through. The hand has to reach to a kettle. It has to hold the kettle. It has to move on to the teapot. It has to warm the teapot back to the kettle, and so on. And, we can understand that each of these represents sort of a different context, in the sense that there's a different dynamics involved when you handle a kettle or a teapot compared to when the hand's in free space. And we as humans could label these, say, these green ones are the ones where the hand's in free space. The cyan ones are the hands in contact with the kettle. And within these contexts, we can think of states as well changing. So as you pour the water out of the kettle, it changes the properties of the kettle in your interaction. And similarly, as you swish that teapot around, it changes the dynamics. And so humans spend that sort of lifetime continually learning, storing, and refining a large repertoire of motor memories. So, we have to form many skills over our lifetime. And the key question I want to address is, what principle underlies how our continuous stream of experience is segmented into separate memories? And I want to point out this is a hard problem for humans or even robots. And there's certain constraints that a principle we're going to develop has to address. That tasks we experience in sequences. We don't sort of batch things. Things just go continuously through life from you're born till you die. You experience things in sequence. Tasks can be repeated an arbitrary number of times. The number of tasks you're going to experience in your life is unknown and unbounded. You probably have a limited ability to store data to process offline. So most of what we're interested in doing online streaming of data and inference. And critically, neither task nor the boundaries between tasks are labeled. So all you get is a sensory motor experience, but you may want to break things down. And the principle I'm going to try and persuade you is the right way to think about this problem is that contextual inference becomes the core computation we have to think about to deal with this problem. And I'm going to talk about the model we've developed called the COIN model, which stands for contextual inference. And we've also called it COIN because it's a fully Bayesian probabilistic model. So we like the idea of the COIN bringing in that probability nature. So I need to be very clear what sort of motor learning I'm going to talk about, because there are many forms of motor learning that we think about when we think about humans. And I'm not going to talk about most of them. So, there's strategy learning. What's the right way to tie a shoelace is some problem. There's skill learning or variability reduction. How do you move your hand to keep the noise low? There's sequence learning. There's optimization. What's the right way to serve a tennis stroke? And there's adaptation. How do you adapt your motor outputs to deal with, for example, changing dynamics? And I'm going to focus totally today on adaptation. We work on all these other things, but the model we've developed today is really about motor adaptation. And really the question is, over the course of your lifetime, you have to handle many objects in many environmental situations with different dynamics. How do you pass all that up? Now, here's a disclaimer which may turn you all off. The model we're going to make is incredibly simple and abstract model of motor adaptation. It's going to deal with scalar states, scalar observations, and scalar action variables. It's going to work on a trial by trial level, but I want to persuade you that even though the model looks really simple, the computation ideas are applicable to much more complex models of motor learning. And I think you'll see that even working at the scalar level with single scalar inputs and outputs and observations, it's actually still quite a complicated model and a rich model to understand. So I'm going to go through the details of the COIN model, and then we're going to describe tests of the model and experiments we've done, as well as explaining classical motor learning results. And then I'll briefly mention how we think contextual inference is more important than just in motor learning. It's more general to biological learning. So this work is primarily done by James Hill, the very talented PhD student and now postdoc. He really developed this all. Matty and L'Engle and I went along for the ride, and it was a joy to be involved in it. So I'm going to first of all describe the generative model. So I'm sure those who are Bayesians will think this way. This is the way we think our brain interprets how data is generated for us by the world. And the idea is that the world can be in a discrete number of contexts any time. You can be a blue context, transition to a red context, then an orange context. And a context is sort of a latent task or environment. You can think of it as different objects. Maybe this is the teapot, the kettle, the hands in free space. Okay, so there's transition over time, there's context. And they can emit observations. And there are two sorts of observations you get. One is a sensory cues. And sensory cue is an observation that is not directly related to task performance. So it could be the visual appearance of an object, the visual appearance of a kettle or a cup, or so on. So context can be associated stochastically with sensory cues, but critically, contexts are also associated with states. So for example, if this is the context for a kettle, this would represent the state of the kettle, which can evolve over time. It can get heavier, it can get lighter. And each context is associated with its own state, which evolves in a time-varying dynamical system over time. And finally, what you get to experience when you move is state feedback, which is effectively a noisy observation of the state of the active context. So if the blue context is active, you get to experience the blue state. But if here, when the orange context is active, you see that you don't experience the blue or the red state, they're gray, you experience only the orange context as output. Okay. And so the hard problem the brain has is it gets a stream of sensory cues and state feedback. That's all it gets. That's all you get to observe of the world. And from that, you want to infer everything that's going on at these higher levels. And that's a fundamentally hard problem. So we're going to pose motor learning as inference in this graphical model. So let me be clear about what you have to estimate. You have to take two different sorts of things. You have to estimate variables and parameters. The variables are things you believe are going to change in the graphical model. For example, which context is currently active, or more specifically, can I estimate the current context probabilities? How probable is it I'm in the blue, the red, or the orange context? And what's the current state of each context? So those things are expected to change, and your inference about them will also change. Then there are parameters in the model, things which are fixed in the model and don't change, but because you're doing inference, your belief about them will change, such as how many contexts have I experienced? What are the context transition probabilities? What determines the Q probabilities? And what are the dynamics of each of these state transitions, which can each be different? And again, you want to learn those through experience. So to really make this a good, well-founded model, we have to put priors on everything we care about. So I'm going to describe briefly the priors we put on them, which lead to the number of parameters we're going to have to fit to date. So the first prior we have is on the state transitions, the context transitions here. And I think we put something called a sticky hierarchical Dirichlet process prior taken from machine learning literature, which has 3 hyperparameters. So it's a non-parametric model, meaning that we don't have to specify how many contexts there are. The number of contexts can grow in a principal way with time. It's hierarchical, which means there's generalization of information between contexts. So it does nice generalization. And the way it really starts off is the hierarchy basically specifies the global transition properties, really how common are each of the contexts I have experienced. So it's a stick breaking algorithm, which tells you, for example, the blue is the most common context. I might have one which is less common, and the red is less common, and so on. So it gives you the distribution of how much time you think you're going to spend in each context. And that's governed by one parameter, which there controls how sort of symmetric or asymmetric these are. Another parameter then effectively generates the transitions from this, or the prior and transitions from context and to, and they're generated in a way that they obey the global transitions. That's the critical part. And finally, we also make them sticky, that you tend to want to stick in the same context. So we add a diagonal element to all that. And that gives us a very flexible prior over the context and transitions. And we apply a very similar prior to the Q emissions. The only thing which is different is we have stickiness now, which doesn't make any sense. But again, there's global cues. Some cues, for example, are more probable than others. And then we associate cues with different contexts using this hierarchical Dirichlet process prior. And importantly, we're not solving a vision problem here. In this model, the cues are going to be discrete. We're just going to give them labels, 1, 2, 3, 4, 5. We also need priors on this dynamical system, how the state evolves. We put the simplest thing we can, that the state of the jth context at time t decays away from the previous state, can have a drift parameter, and has noise. and we put sensible parameters on those. On the decay, we have a truncated Gaussian between 0 and 1, and on the drift, we have a Gaussian centered on 0. And actually, the drift is what allows us to have long-term memory. By learning a drift, effectively, the state can maintain memory over long periods of time. And finally, the state feedback you receive is the state of the active context plus Gaussian noise. So overall, the number of free parameters we have in the model is 7 or 8, depending whether a particular experiment has sensory cues or not. So it's not that many parameters, and there's a richness to the model. Okay, so let me just talk about the inference. The inference is rather interesting in this sort of trial-by-trial task, in that there are 2 steps to every trial. Before you move, you get to observe the sensory cue. Okay. After you move, you get state feedback. And so the inference process actually works in 2 steps. There's some inference based on before you move and inference based after you move. So you come into a trial with a predicted belief about different contexts, given the context you believe at the last time step in your belief about transitions, and given the sensory cue experience. So we're going to predict before we move which context we think we're in. And critically, we can use that to weight the states of all the contexts we've currently developed. So basically, the way we express our memories is in proportion to the belief we think those memories are appropriate. So in this case, you've only got a blue memory here. You haven't got any other memories. And you've only got a novel context memory. You always represent the memory for a novel context. And you'll weight those based on how much you believe each is active. And that generates your motor command before you move. You then generate your movement and get state feedback. And now you can recalculate your belief of that each context was actually responsible for the movement you've just made. So now we estimate the probability of the context giving both the cue and the state feedback. And critically, this can be used for 2 things. It can be used to decide when should I create a new memory. If, for example, the novel context has a high responsibility compared to memories I've already got, I could spawn off a new memory for the situation and then track the state of that. And finally, the responsibility is also gate learning. You want to update these based on errors, for example. And again, we're going to use the responsibilities to gate how much learning happens to each of our memories. So in this model, we do it coherently with memory expression, memory creation, and memory updating. Okay, and the details of how we do this is we do it with particle learning, and that one line hides about 8 months of work to get this to work properly. Okay, so let me give you a toy example of the model in progress. So here's a toy example. You get to handle a bunch of identical cups. Okay, so they have the sensory cue for all these cups are the same. And here I'm showing you the sense weight of the cup. So cup 1 is light, you then go to cup 2, which is heavier, back to cup 1, to cup 3, which is heaviest. You empty it of some water, back to cup 1. And then you go to a sugar bowl. And the sugar bowl has a different sensory cue and weighs the same as cup 2. And so the input we're going to give to the model are the discrete sensory cues, Q1 and Q2. And we're going to give it a noisy version of the state feedback. So we give it that. So that's all that goes into the model are these purple dots and Q1 and Q2. And the first thing the model does is it estimates at each point in time how probable is that I'm in a novel context. You know, is my novel context, my prior, a better explanation of what's happening now than all the memories I've got. And to start off with, the novel context probably is high since you have no memories. So you generate a memory for cup 1 here. When you come to cup 2, it's not novel enough, in this case, to generate a new memory. When you go to the red with cup 3, you generate a new memory. And interestingly, even though the sugar bowl weighs the same as cup 2, because it has different sensory cue for these parameters, you generate a third memory. So over the course of this experience, you've generated 3 memories of the states. And every time you generate a new memory, you have to track the state of that memory in a fully Bayesian way. So that's shown here. This shows the state of each of the contexts. So you start off with a blue context, which is going to track this weight. Because you didn't generate a new memory, you'll have to update the state for cup 2, as you see here, back for cup 1. But because you generate a new memory for cup 3, you can maintain your memory for cup 1 here in blue, while you generate a new memory for cup 3. And finally, here you can see the memory for the third context for the sugar bowl being developed here. This is a full Bayesian representation. This is the full posterior, not just point estimates. The gray background you can see is the prior for novel context. So you generate these three contexts, they track the states, and now you have to decide at each point in time, what motor output should I generate? And as I've told you, you should weight all your memories by your belief that they're appropriate before you move, the predicted probabilities. And so what I'm showing you here is those predicted probabilities. You start off only expressing the blue context, but as you generate a new memory, you start to express the red context more and the blue context less, and so on. So if we multiply each context by its predicted probability, we get the motor output, which is shown in the full posterior in the mauve, and we take the mean of that, which would be the motor output. So if we were running an experiment, the thing we would measure from a participant is this blue line here, showing that it does a reasonably good job of tracking, the behavior and the weight of the cup. But there's some interesting features here. One interesting feature is that this learning, which looks slow when you learn cup 3, looks like you're somehow slowly adapting your behavior to cup 3. But actually, that's not really the case. Because if we look here, what's driving this slow learning here is actually you're slow changing your belief that you're in a new context. You've actually learned the weight of cup 3 instantly, shown here. So this is tracking cup 3 perfectly. What's driving this slow learning is that you're not willing to believe that you're going to stay in that context. Okay, and so this is actually apparent learning, because what it is it's not really a fundamental change in your belief about the state of that cup. It's really the way you express what you have, which leads to this apparent learning. And that's quite different, for example, from this behavior here, when you adapt to cup 1, which is driven purely by changes in your belief about the state of cup 1, which I'm going to call proper learning. And so this model makes a really interesting distinction between two forms of learning you can have. Proper learning when you're changing your belief about states, and apparent learning when you're just mixing learned behaviors. And I'll come back to that next slide. And what you're going to see is a lot of motor learning is actually apparent learning, mixing of behaviors, rather than true learning, changing your belief about states. After you move, you get state feedback. You now can calculate your responsibilities, which are shown here, and we're going to use those to update memories. And so when the red responsibility is high, you're going to update memories rapidly. And when the red responsibility, for example, is low, you don't update it since you're not observing, and it's going to diffuse out. And so this model deals very nicely with the creation, expression, and updating. So just to hammer home this idea about proper learning, here are 3 simulations of the coin model. Here is the perturbation shown in black, and here is the motor output shown in cyan. And for these 3 simulations, the motor learning looks identical. Yet what's going on under the hood is fundamentally different depending on what state the learner came into this experiment with. And if I asked you which of these is proper learning, you wouldn't be able to tell me just by looking at this behavior. So it turns out that the left-hand one is proper learning. You come into the experiment this time with 1 memory for no perturbation. And when you come to this perturbation, you adapt that memory and you just fully express that memory throughout, leading to full proper learning. In contrast, this learning curve is completely apparent learning with no proper learning at all. In this case, the model came with 2 memories, a memory for perturbation of 1, a memory for perturbation of 0. It was expressing the memory for 0. And as it goes into the learning curve, all it does is it changes its expression by changing its belief about which context it's in. And that leads to this learning curve, which is identical to this, but in a fundamentally different mechanism of learning. And finally, which I'm sure happens in most cases, you can get a mix of proper and apparent learning. In this case, the participant came with 1 memory, but when the perturbation turned on, they generated a new memory, which had to learn the perturbation, and similarly, they had to change the mixing proportions. So it's important to realize when you see learning curves, they can arise from 2 different sources, mixing of memories or actually changing the memories themselves. So, okay, and what I want to do is now show you some tests of the coin model. And we need to find some sort of data sets which make sort of interesting and maybe counterintuitive predictions. So I'm going to tell you about experiments we do in motor learning. And since we're interested in adaptation, the way we study that is to ask how do people adapt to novel dynamics. And so to do that, we typically ask people to reach, where we basically change the relationship between their motor commands and their consequences by applying different dynamics to them. Now, this has been done in many ways. You can put weights on people's wrists. You can put them in 0 gravity. You can give them spinning wheels, gyroscopes to play with, put them in rotating rooms. And people have done studies in all these. But for our point of view, they don't give us the precision we need to control the dynamic environment. So we go to a lot of effort to basically give people novel experiences in the lab. From our point of view, we don't want to give people tools they might have seen outside. We want to give them experiences where we can be pretty sure they haven't seen before, so we can look at de novo learning. And to do that, we build robotic interfaces in our lab, which can both track and perturb the movements in a computer-controlled way. So we're using robots not for robots, but we're using them to perturb people and study people. And so here's a typical experiment. This is actually a participant in one of our rigs. They're holding onto a handle of a robot. And all the experiments I'm going to talk to you about today are using the two-dimensional robot. So it's a planar robot. It can move in the plane. We can track the movement and apply forces, updating them at 1,000 hertz. And so we can create arbitrary dynamic environments. And we also use a very poor man's virtual reality, sort of monitor facing downward, a mirror facing upwards, so they see targets and feedback of where they are in the plane. So we can create visual feedback in the plane, and we can also perturb their movements. So here's a typical thing we might do. We start with the robot off. We call that a null field. P stands for perturbation. 0 means there's no perturbation. And they very happily move and make lovely straight line movements. But then we can apply forces to them and look at how they learn them. And a force we particularly like, and one used by others before us, is one in which the force in the x and y direction applied at the hand is some gain times this matrix times the Cartesian velocity of the hand. And if you plot that out as a vector field, what you get is this. So if you don't move, you get no force. The faster you go, the bigger the force on your hand. And the force always acts, at right angles. We don't want me to do that. Right angles to your current direction of motion. So if you move away from yourself, you get pushed to the left. If you move to the right, you get pushed away from yourself. And we call this a counterclockwise viscous curl field. So if you were to make this movement, you're going to get perturbed to the left. And we're going to call that P+. And we can change the gain here to be an opposite sign, and then you get P- pushing you the other way. So you're going to hear a lot about P0, that's no field, P+ pushing you one way, P- pushing you the other way. And if you look at the data, subjects start off making lovely straight movements. If you apply P+, they get perturbed off. That's the trajectory. After half an hour or so, they make lovely straight line movements. And in fact, they think the robot's been turned off. They've internalized the force field and don't even perceive it in the same way. And if you turn it off in P0, you see an after effect. And we can quantify this in many ways. You can quantify the deviation from a straight line. And if you plot that, over the course of an hour, you see that people reduce their error. We don't use this measure of learning for two reasons. One is we can't easily transfer this into like a measure of how much of the field they've learned. And it's also contaminated by co-contraction. You can just stiffen up your arm to counteract that. And we really want to look at the feed-forward compensation to this force field. So a technique's been developed in the field where occasionally on probe trials, maybe 1 in every 10, rather than apply the force field, we apply a stiff one-dimensional spring, a channel, which constrains the hand to move straight to the target. So from the participant's point of view, they have a lovely movement straight to the target. They think they've done a great job. But from our point of view, we can measure the forces they produce into the channel wall as a measure of what they anticipated the force was going to be. So maybe this is the force they produce into the channel wall as a function of time. We can calculate what the ideal force would be to compensate for the force field had we presented it. And then we can regress them to get a measure of adaptation. So maybe this is 30% adaptation, this will be 50, this will be 75%. So now we can actually measure how much have they adapted. And I'm showing you now the same data as this, but now on the channel trials, they start off with no adaptation. And in this case, they get to about 70% adaptation, okay? And then they de-adapt, okay? And we don't have so many exposure channel trials as we do perturbation trials, but it's a very useful measure. Okay, let's get to an experiment, which we're going to try and explain with the coin model. This is a sort of famous result called spontaneous recovery developed by Maurice Smith. Bring participants in, you give them P0 for a while so they get used to the robot. You then give them P+ for a while so they adapt to that force field. And then you briefly give them P- with the idea of bringing adaptation back to 0. Okay, that's the idea. And then you put them to a long series of channel trials just to measure adaptation. And what you might imagine is, having adapted and de-adapted, if they're back at 0 here, putting them in channel trials, they would just stay there and just generate no force into channels, giving you de-adapted them. But that's not what happens. Here we see the adaptation. Here we see the de-adaptation. There are no channel trials in the de-adaptation phase. That's why there's no data. Actually, in this case, for this group of subjects, after de-adaptation, they were actually negative in the force they produce. So you might think they would just drift back to 0. But actually what they do is show spontaneous recovery. They transiently re-express the P+ adaptation before decaying away again. Okay? And there's a classic model which has been used to explain this result called the dual rate model. Please don't put too much of your brain power to understanding this model, because I think the model's wrong, as I'm going to show you. But it's an interesting model, and one which is incredibly popular in motor learning field. What it says is there are two processes governing learning which compete to learn. There's a slow learner and a fast learner. And so in this very simple situation, the slow learner updates its belief about the force field by slowly decaying and slowly learning based on error. And the fast learner also updates its belief about the force field, but it decays quickly and effectively learns quickly. And then the output is the sum of the two. So they're going to compete to learn this field. And so the output, which is the sum, learns, unlearns, and then shows spontaneous recovery. And the reason for that is if we look at the two components, the fast learner starts learning, but then the slow learner takes over. So by the end of this phase, it's mostly the slow learner which is underlearning. Then when you de-adapt, it's the fast learner that de-adapts quickly. So even though you've got no motor output, the slow learner is positive and the fast learner is equally negative, so they sum to zero. When you go into the channel trial phase, there are no errors anymore. You're making lovely straight movements. So all you do is decay. And because the fast learner decays quickly, it reveals effectively the slow learner, leading to the appearance of spontaneous recovery. Now, critically, this dual rate model is a model of proper learning. The only things that can happen here is if you change your belief about the states. But let me show you what happens if we run the spontaneous recovery paradigm through the coin model. So all we do is, there are no sensory cues here. All we do is take these purple points and we run them through our model. You start off with one context for P0. You generate a new context and a new state for P plus and a third one for P minus. So you've generated three memories by the time you come to the channel trial phase. And during the channel trial phase, they sort of maintain or decay away a little bit. But here are the predicted probabilities. You start off expressing just the blue. As you go to P plus, you begin to express the P plus memory, the red memory. But when you get to the channel trial phase and there are no errors, because you've experienced P plus the most overall, you begin to believe that you're going to go back into P plus. It's the most common context, and therefore in the absence of other information, you think you're going to transition back. And therefore you begin to re-express this red memory, which leads to the spontaneous recovery. Okay, so this is really different. The coin model, we're seeing changes in motor output occurring without changes in internal states of apparent learning. There's very little changes in the internal state here. It's really the belief about which context I am which is driving spontaneous recovery. In the dual rate model, you can only get changes in motor output by changes in the internal state through proper learning. And so we can come up with a new experiment to distinguish between them. If we can give strong evidence that a context has returned, then the coin model should really re-express that memory in a very abrupt way. And the way we can do that is just change this paradigm very slightly. So at the beginning of the channel trial phase, we give two P plus trials. Okay, this leads in the coin model to a rapid belief that you're now back in that context compared to a slow increase, and leads to a prediction you should get a vote recovery rather than sort of slow increase and decay. You should abruptly get it and decay. However, two trials is not enough to get substantial proper learning. And therefore, the dual rate models you're going to see will struggle to explain this data. So here's the data from two groups of subjects. This is spontaneous recovery. And we can see that we get this nice behavior of spontaneous recovery and decay. Here is the evoked recovery group. If we fit the dual rate model, there's it can explain spontaneous recovery because the model was developed to explain that, but it can't explain evoked recovery. Basically, in order for it to explain this rapid increase here, it has to use the fast process, and the fast process decays away very rapidly. So there's a really qualitative mismatch. If we look at the coin model, we can explain this data very nicely. And if we do a group level BIC, since we have more parameters in the coin model, it's substantially better. So it suggests to us that context estimation really controls memory creation and expression in spontaneous and evoked recovery. Okay, and we think the dual rate model is not the right model. It's sort of a mechanistic model, whereas the coin model really is a sort of Bayesian normative type model. I told you the reason you return to P plus is because you've experienced it the most. So a prediction would be that if you experience P plus even more, for example, add in more trials of P plus, then our prediction is you should have even greater spontaneous recovery, because now you're going to more rapidly return to it and really believe you're back in P plus. So that's the model simulation. And in fact, another group have run exactly this experiment. And what they find qualitatively is exactly what we see, that you increase your spontaneous recovery if you experience this P plus for a longer period of time. So the magnitude of spontaneous recovery is sensitive to the frequency or statistics of context in the environment. Another nice feature that we know is that it's very different to learn a perturbation gradually than abruptly. So if you apply a perturbation abruptly, such as this, and then turn it off, you get very different decay than if you introduce a perturbation gradually and then turn it off. So it's been shown, and this is not our data, that if you learn it abruptly, switch it off, it goes away quickly, your learning. You decay back to baseline. If you learn it slowly, even though you've learned it equally well, it decays away slowly after that learning. And if you run our model on this paradigm, we get exactly that. We're not trying to fit this at all. This is just using some arbitrary parameters. Again, the decay is slower when you've learned it. And now I'm going to try to explain to you, by explaining to you what's happening inside the coin model, why this happens. And it's sort of like counterintuitive and sort of interesting. So, I think what I like about the coin model, these explanations which aren't obvious on the surface, well, to me anyway. When you have an abrupt perturbation in the coin model, you generate a new context for the perturbation. So here you start with P0. For the P plus, in this case, you generate a new memory. Okay, so that when you go into the de-adaptation phase, you've maintained your context for the null. And therefore, all you have to do is switch back to it once you realize you're back there to abruptly decay. So effectively, this salmon line is driven effectively by apparent learning where you're de-adapting really quickly because you're switching back to something you've maintained. In contrast, if you bring a perturbation in gradually so that errors don't get big, you don't get a second memory. You basically adapt your first memory, as shown here. So now the first memory gets adapted. But when you turn the perturbation off now, you generate a new memory for the unperturbed condition, shown here in red. But you've been in the blue memory a long time now, and therefore it takes you a while to believe you're going to stick back in that red memory. Okay, and that leads to effectively a slow transition here back to the red memory and a slower decay. Okay, so again, we can explain these differences in de-adaptation for different types of perturbation by thinking about memory creation, memory expression, and memory learning. So large errors are important for memory creation. If you maintain the errors small, you'll get proper learning rather than a new memory. So I've talked a lot about memory creation and memory expression, but memory updating is also of importance to us. And in single context models, typically some state estimate is updated from the previous state estimate by some error and a Kalman gain. But life becomes more complicated when you're in a multiple context model. Again, each context has a state and it's updated from its previous state, again by the error it receives, its Kalman gain. But now it's also modulated by the responsibility, how much you believe that context was responsible for the movement you've just made. And so the prediction here is that every memory you have should be updated in proportion to its responsibility. So unlike many models of motor learning, when you only update one memory at a time, our model suggests you should update them all. Now, in reality, most memories will have a responsibility of 0, so you won't update them. But we're going to create a situation experiment where we make sure that more than one memory has a responsibility which is non-zero. And I'm hoping to convince you that you update more than one memory at a time and you update them in proportion to their responsibility. This is a complicated experiment. So that's our prediction. There are around 24 participants on a memory updating experiment. And the way this works is we want to engender in the person's brain 2 contexts. And we want them to associate each context both with a perturbation, state feedback, and with a sensory cue. So this is the first time I'm really bringing a sensory cue in. So the context 1 is going to be P associated with a plus, a perturbation in one direction, and a sensory cue 1. And the other context is going to be P minus the opposite perturbation and a different sensory cue. And the sensory cue we need, I'm not going to go into much detail, but the sensory cue you need is really, you handle a bar which moves with you, and you're told on some trials to move the right point of the bar to a right target, on other trials to move the left point of the bar to a left target. Now, both of those require the same movement, but it's a different sensory cue because it's a different target at a different point you're controlling. We know from previous experiments that sensory cue is really good to allow you to learn different contexts. Okay, so P1 plus and P2 minus are different feedbacks and different cues, and we basically train people on these by randomly interleaving these trials so that we hope by the end they have 2 memories in their head and one's associated with plus, one with minus, and one with context 1 and one with context 2. Having trained them on that for many, many trials, we're then going to ask how much do they update a memory to a single exposure trial. Okay. And the exposure trial we're going to use is either one which is one they've seen before. So they might get a P plus with Q1 or a P2 with P minus with Q2, or we give them conflicting things such as P plus 2 or P minus 1. And the reason we do that is that's going to confuse them as to what context they're in. And hopefully it'll allow them to update both memories if they're not sure which memory they're in the appropriate way. So by creating this artificial, it's not really artificial. I mean, you can see a big object which is light and a small object which is heavy. It's a similar sort of idea, but we're going to try and make them have intermediate responsibilities so we get intermediate update. So we give them exposure, and the way we're going to measure learning is before and after that exposure trial. We're going to give them a channel trial where we can measure adaptation, and we're going to give them sensory Q1. So we're going to measure what's in their brain for context 1. And we measure it before and after, and the difference between before and after is our single trial learning for context 1. So let me try and give you an idea of how the model works. Before you move, you see the sensory cue. You see whether I'm going to be moving this point to this cue or this point to this, but you don't know what the force field is going to be. And so before you move, your belief based on the cue alone is if you see Q1, you're going to have a high belief you're in context 1. If you see Q2, the subscript, you can have a low belief. When you move, you now experience the force field. And so now you can calculate the likelihood. If I experience the positive force field, I'm more likely to be in context 1. If I experience a negative, I'm low likelihood. So combining these together in a nice Bayesian way, it predicts that single trial learning should show this gradation for context 1. If it's extremely consistent with context 1, I should update my context 1 module a lot, memory. If it's P2 minus a little, and these should be intermediate. There's a reason why this one is hard than that, which I won't go into, but it's built into the experiment. We look at single trial learning, that's exactly what we see. We see this graded updated for memory 1. And because the experiment is completely symmetric, had we probed memory 2, it would be just the opposite. We can sort of guarantee that memory 2 has been updated in the opposite way. So this suggests to us that you're updating multiple memories, at least 2 in this case, in proportion to their responsibility. And the last thing I want to tell you, really, is that classical paradigms, which we explained in different ways, are all apparent learning. So for these, I've told you all those subjects. We've run roughly 30 subjects, and we fit individual subject data. We're now going to take the fits of those and just simulate these classical paradigms. So we're not going to fit the paradigms. We're just going to simulate them from those and average the data. If you learn something once, go away and come back and learn it again, you're faster the second time. And people tend to think that maybe you've cranked up the learning rate. So here's an example. You do spontaneous recovery paradigm twice. I'm just plotting what happens in the learning of the P+. The second time you do it in salmon color here, you're faster to learn it. We run our coin model on this. That's exactly what we get. But importantly, there's no change in the Kalman gain, which is our measure of learning rate, or in the states the first or second time. That is not driving these differences. What is driving the difference is your predicted probability that you're in a new context. That having experienced this context 1, you come to it the second time, you're more willing to believe that you're in a new context, and it's your belief in a new context which drives the apparent faster learning. So this is all driven by apparent learning, the mixing of previous things. Similarly, anterograde interference. The longer I experience P+, the harder it is to learn P-. Is all driven again by apparent learning. So this just shows if I learn P+ for a little time and then get a P-, I'm quick. But if I do P+ for a long time, then I'm slow. Our model captures that behavior. And again, there's no change in the learning rate or the states. It's all driven by the fact that the longer I experience P+, the less I'm going to believe that I'm going to go to another context and stay there. And finally, volatility. If you put people in an environment which switches between P+ and P-, either very rarely or very often, and then you measure single trial learning, you find in the environment which is very stable, they increase their single trial learning. In a volatile environment, they decrease it. That's been taken and measure that they're adapting their learning rate to the volatility. Our model reproduces behavior, but there's no change in the learning rate, no change in adaptation. It's all got to do with that you learn the same amount for a single trial, but if you're in a volatile environment, you're not going to express it on the next trial because you don't think that context is going to hang around. Whereas if you're in a stable environment, you're going to express it more. So it's all driven by your predicted probability that that context will be maintained to the next trial. So apparent changes in learning rate are driven by contextual inference. I'm not going to go over this because I know I'm running out of time, but there are many other models which can't explain this because they either failures in the generative model or the inference process. They lack many features of what we can do in the coin model. And I just want to point out, and we're writing a review paper on this at the moment, contextual inference is really central to many forms of long-term memory in cognition of both humans and non-human subjects. Different fields have used different words. So conditioning, reward-based learning, and perceptual episodic memory all think about context. When you train a mouse to respond to a tone and shock, they freeze, and then you untrain them, you haven't set them back to zero. You've generated two new contexts. Similarly, reward-based learning, and similarly, when you watch a movie, you break the movie down into different contexts or different parts automatically. And we think actually the contextual inference is core to all of biological learning, and we're trying to see whether the coin model can be used as a unifying way to think about all these forms of learning. So in summary, contextual inference is a key computation. It's principled in its Bayesian, it's comprehensive. The model at the moment is simple, but for us it's complicated enough. You can make this infinitely more complicated in terms of making a combinatorial context. You can think about how you might merge contexts or delete contexts, or you can reorganize memories during sleep, and that's all for the future. But we think it unifies many disparate data sets which require different models. And it makes a clear distinction between apparent and proper learning. And I really want a big shout out to James Hill, who was really the driving force behind that, and my funders. Thank you so much.
Brilliant. Thank you so much. There was a lot of content in that, a lot to take in,
yes.
And some really fascinating insights. No, it was fantastic and very understandable even to new people to the field like myself. So thank you very much. And please do post your questions on the chat, and we'll have a few questions for Daniel and then bring in the rest of the panelists we've had from the earlier session to have a bit more of a panel discussion. One question we have on the chat is, do you have any hypothesis for perhaps the mechanical or the neural explanation for how this is actually implemented in humans or animals?
Sure. So we are looking at that at the moment in two different ways. So I'm collaborating with Mark Churchland's group, who does motor cortex recording in monkeys. And so we have monkeys doing a context switching task. So it's a nice task because they get to basically do a Pac-Man task, so sort of chasing a thing on the screen by pushing a joystick forward and back. And in one task, the gain of the joystick is +1, and the other task is -1. Again, they're doing an isometric task and they're just generating force. And the nice thing is we can change the path so they generate exactly the same forces at hand under the two different contexts. And the belief was going to be that motor cortex wouldn't care, it just cares about the force. But it turns out it really cares about the context. You get completely different representation of motor cortex if it's doing the task under a +1 and a -1 context. And that's in stark distinction if it's doing it under a positive context where the gain is 1 or 0.5. When it does that, it generates the same output. So it seems to be that the motor cortex seems to separate out context in that way. So that's one thing we're doing. We're trying to recruit a postdoc at the moment to work with Mate Lengel and Guillaume Anakin in London. We want to generate neural network models of contextual inference. So that's something we're really keen to think about on the theoretical side. What are the right ways to build a model which can do this contextual inference in real time? So we're really interested in that. We don't know. At the moment, we're recording in basal ganglia, which we think may be the thing which switches you between contexts. But again, we don't have the full results of that. But it's exciting to see that behavior in the monkey.
Yeah, thank you. And one question I had about this memory, as the body changes, let's say you age or you grow or you have an injury, how does that also affect the memory? Does that also come into some proportional weighting or affecting the memory? Or?
Absolutely. So, I mean, you could even think about fatigue. The body changes with fatigue. Do you have different memories for different fatigue levels, and do you switch between them, or are you always adapting one model to account for fatigue? And those are interesting questions. As you grow, if you build one thing we don't really do so much here is the repurposing of memories. All our memories rather stupidly start from the novel one. They don't spawn off a current memory. And we're interested to think of, is that really the right framework, or should we be thinking of spawning memories off from the closest one, which novel? We don't know. I also think we need to think about sleep. So we know that during sleep, memories get reorganized. People actually get better at motor tasks sometimes over sleep. And the question is whether you can actually reorganize these memories in sensible ways so that you don't just keep proliferating memories. But we don't know the answer to that. They're all open questions.
Yeah, please do keep the questions coming in or raising your hand. And a very nice question from Barbara. Do you maybe have an alternative way to think about this short-term versus long-term memory? in opposition to the duality approach that you mentioned.
Yeah. Okay. So certainly in this model, there are short and long time courses which come into it naturally. Anyway, so long-term memory really in this model is learned by the drift. Once you learn a drift, even if you don't observe that context, for a long period of time, because you've got retention and drift which goes in opposite way, you come to a new level. So that's how you can maintain long-term memory. And then short-term things really happen in terms of the predicted probabilities, which can change very rapidly. So I think there still are multiple timescales in this. You just don't have to build them in. I think it's more interesting that way, that they come out naturally out of it. Thank you, Barbara.
And I think our final question before we'll move on to the panel discussion is, I think the experiment you showed, there was a mixture of using visual information and also proprioceptive information to do the learning. And how does that affect the learning or the memory creation if it's different types of sensory information?
So I think they both come together through the contextual inference. So effectively, you're using proprioception and vision to estimate context. So that's the way you can unify them in this sense. In this particular one, the error all comes from proprioceptive. Okay, so the error is driven by your state feedback, but contextual inference is driven by both the sensory cue and the state feedback. So that's how they come together. And in fact, with force field learning in our experiment, you don't need vision to learn. We learn just as well with your eyes closed as your eyes open. So vision doesn't play a big role in this sort of dynamic learning task. It plays an important role if the force field's changing and the vision's changing. You can use the vision to switch between different dynamics. It's used for the context.
So sorry, actually, couple more questions. Sorry, it's getting more and more interesting.
That's a very good question.
Very much
Yes, that's a really good question. Yeah, so I think in the end, context, we need to think a bit more about family. So we've been doing some work on, you have thousands of objects you have to interact with all day. I don't think you learn them as 1,000 discrete contexts. For example, I think you learn all cups maybe as one context and then parameterize them by the size and shape of the cup. And yes, evidence for that. So we're beginning to think that contexts have to be parameterized by sensory cues in some way as a proxy to dynamics. So that we know that big objects are heavy, small objects are light, even within a context. And so I think we're beginning to think about that. You could think about context being continuous, but then things, to me, become a bit messy. They merge into them. What's the difference between them and states? So I think one interesting is the combinatorial thing, which we haven't dealt with. How do I deal by combining contexts? I'm on a rocking boat and I'm holding an object. Those are two contexts together. You'd want to combine those rather than have to start with that's a novel context. And again, that's a question for the future for us. Thank you, Jimmy.
Just one point also on reflex action, or so decisions made by the CNS or not made by the brain. Is there a way in this framework which you could incorporate that kind of decision making or that motor response within this kind of visual and sensory learning framework?
So you mean, certainly all reflex, not the shortest reflex, the medium and long latency reflex are very context dependent. So they change with the context, so it's well known that if you're on a platform which is translated back, so it stretches your ankle, you're upright, but if it tilts and stretches that, then you do the opposite effect. So people can learn through the context to generate different slow reflexes, but the very fastest you can't. So I think that would play into this very nicely, that effectively you're learning context dependency to appropriately set gains for your reflexes.
Really fascinating. So thank you so much for your talk and your time there answering questions.